This is Dan Abbott. I'm making this video to discuss determining size ranges for specific classes of fit. This is for the mechanical design class at Southern Maine Community College, and this information is coming from, well, originally from ANSI B4.1, the standard that was published in '67 and reaffirmed in '87. We're going to deal with ANSI standards, not ISO. They use different tables, same concepts. These tables can be found in the shop reference for students and apprentices, which is really a subset of information from the Machinery's Handbook. There's an older version. The current version is the 30th edition of the Machinery's Handbook, and it's published by Industrial Press. If we take a look at the pages about allowances and tolerances, this comes from the shop reference for students and apprentices. ANSI standard fits are discussed, and one of the first things it indicates is that in selecting limits of size for any application, the type of fit is determined first. So in other words, before you can determine the size of something, you have to know what the class of fit is that you want, and then you use the tables to determine the specific tolerance range for both holes and shafts. And we're talking here really about how a hole and a shaft have to be sized so that you either have a clearance, a transitional, or an interference fit. So function is what determines the tolerance range for different classes. And here's some examples, and these examples include ANSI and ISO fits. The ANSI standards are a little easier to remember because they use letters that refer specifically to fit concepts. The metric standards are a little harder to remember because they use, as far as I can tell, randomly assigned letters. And in these cases, all four of these examples are duplicated down here. So up here we have a gear. That's the gear right there, shown in section with a Woodruff key. It's on a shaft. That shaft goes into a bearing, which in this case is a plain bearing or a bushing. And what we have here is three different kinds of fit. At first, a locational transitional fit, and that's the gear going onto the shaft. Locational means that you have a very, very small difference between the hole size and the shaft size, so that there's very little movement, if any. And in fact, a transitional fit can either be a clearance fit or an interference fit. Down here we have an RC4, which is a running clearance fit, and that's the shaft inside the bearing. In this case, the shaft always has to be smaller than the hole in the bearing or in the bushing in order for it to turn freely. And then we have the bushing itself, which is press fitted into some kind of device. And that press fit is known as an interference fit. And the interference fit in this case is so that the bushing won't turn and the bushing won't come out readily. You have to press it in and press it out. And the letters that are significant here are the T, the C, and the N. T stands for transition. That means it's kind of halfway between a clearance fit and an interference fit. And in fact, in most cases, it can be one or the other. C stands for clearance. That means that the shaft must always be smaller than the hole you put it in. And N stands for interference, which means the shaft must always be larger than the hole you put it in. We have a couple of other examples over here. Locational clearance. It's always a clearance, but it's a very small clearance. In this particular case, that bolt has to fit through the part that it's using as a clamp, but you don't want a lot of play in it. Over here we have another LC, and again, that's a locational clearance. It's a small amount of clearance. This is a pin that's linked to something that's going to be pivoting back and forth. So in one case we have a locational clearance. In another case we have a running clearance. The running clearance is on the part that pivots around the pin. And then we have a force interference fit. Force interference means you have a very, very strong interference. It's the biggest. Well, FN2 isn't quite the biggest, but the force interference fits require a significant amount of force, usually a hydraulic press, and at one level heating the parts and then pressing them together. And a force interference fit is meant to be more or less permanent. You don't normally take it apart, although it's possible in some cases to take them apart. Before we calculate some of these classes of fit, a couple of definitions. One, nominal size. Nominal size, and it says name, nominal, probably from Latin, but the French as in nom de plume. The name of the size that's applied to both the hole and the shaft. So suppose you have a 2-inch shaft and a 2-inch hole. 2 inches is the nominal size, not the actual size, and it's not the tolerance size. The actual size is what it measures once it's been manufactured. Basic size comes into play a little bit. It's the theoretically perfect size with no tolerance, and when you identify that on a drawing, you have to put a box around it. And virtual size we'll get to when we deal with GD&T. Now, with classes of fit, every dimension on a print has a tolerance, period. That means that no matter what you have on a technical drawing, either the title block shows a tolerance for the different dimensions on the part, or there's a direct tolerance applied to each feature, and that direct tolerance can be a limit tolerance or a bilateral tolerance or a unilateral tolerance. Two concepts that are really important are max material condition and least material condition. Maximum material condition means a condition under which the part has the maximum amount of material or weighs the most. What that means is that when you have a tolerance, the two different values at either end indicate either a max material condition or a least material condition. If you've got a shaft, max material condition is the top number, the largest that the shaft can be. If you have a hole, maximum material condition is the smaller of the two numbers, the smallest that the hole can be. In both cases, max material condition is going to be used as a starting point for determining the tolerances that you come up with for the other three values. Least material condition is the opposite of max material condition. Least material condition is when a part weighs the least or has the least material in it. So it's the smallest size on a shaft and it's the largest size on a hole. Now the letters that we identified in the ANSI standard, the C, N, T, R, and L, have specific meanings and they're helpful in terms of understanding the function of the class of fit you're dealing with. Something is a clearance fit, that means the hole is always larger than the shaft. The letter C is used to identify clearance. If something's an interference fit, the hole is always smaller than the shaft, but the letter I looks so much like a 1 that instead of using I to represent interference, we use N. Transitional, the hole is smaller, usually than the shaft at maximum material condition, and larger than the shaft at least material condition. So in other words, at one end of a transitional fit, you have a slight interference. At the other end, you have a slight clearance. Transitional is represented by the letter T. Running means you've got a situation where parts have to move, rotate, slide, and that means you need a significant amount of clearance, at least based on a class of fit. The letter R is used for running. And then locational means that the purpose of this class of fit is to locate parts accurately. And there are two kinds of locational fits. You can have a locational interference fit, which means that the parts have to be pressed together with relatively light pressure. And that means that they are going to be perfectly located. They can't move around. Or you have a very slight clearance. And if you have a very slight clearance, that means you've located the parts accurately, but there is still some small movement. In between them is the transitional fit, which means it could be one or the other. And force means you have to use force and or heat in order to put the two parts together. The only other thing you need to know before we actually start doing some calculation is the notion of a basis. A basis is, what do you start with? You either have a hole basis or a shaft basis, and it really comes down to, are you creating the hole first and then matching the shaft to the hole, or are you creating the shaft first and matching the hole to the shaft? In many cases, the question is really, are you purchasing a part that's already been manufactured? And in some cases, it's, things like a shaft, if you're going to have to go through multiple holes, and you probably start with the size of the shaft. Generally, when you're calculating classes of fit, you start with the hole. So a hole basis is a standard, and that's what all the tables are based on. Shaft basis has to be calculated from the hole basis numbers, which means you have to shift all the numbers if you're going to have shaft basis in order to come up with the right dimensions. So in the ANSI system, there are 5 categories of fit. Running clearance, which is the biggest amount of clearance, and there are 9 classes within that category, RC1 through RC9. LC stands for locational clearance. That's a clearance, but it's a smaller clearance. There are 11 classes of locational clearance, 1 through 11. LT stands for locational transitional. That means that it could be a little interference, it could be a little clearance. It depends on whether or not the parts are manufactured at max material condition or least material condition or somewhere in between. LN stands for locational interference, and locational interference fit is meant to locate parts accurately, but with a slight interference, so there's no question about the location. It can't move at all inside the hole. FN, force interference, is a much bigger interference, and that's the one that requires significant force or heat. So let's take a look at calculating each of these. Going back to my opening slide, one of my opening slides, we're going to take a look at this gear and shaft and the bush bearing. Now the gear and shaft and the bush bearing has 3 different kinds of fits identified, LT1, RC4, and LN3. So we get down to calculating the fits. First, you have to go to the tables, and I'll show you what those tables look like in the book, and I'll then come back to this slide. The table for the RC4 fits is on page 214 of the student reference. The chart's printed sideways, so I'm going to turn that page and take a look at it in the table. So here's the column. It has nominal size range. We come down to the row that includes the size we're interested in. Then once we get that, we come across all the way over to the column that deals with the class of fit we want. RC1, RC2, RC3. We'll bring that back so you can see the RC4. RC4 is right here. So the class of fit is going to be determined by those three cells right here. The first just indicates what the maximum clearance and maximum interferences are. But as far as calculating the size you want each part to be, these are the numbers you're going to use to determine the tolerance range. So we have a 625 thou nominal size for both the shaft and the hole. Now they can't both be made that size, so now we come over here. We're looking right here where it tells us for the hole, in order to determine the tolerance range, we're going to start by adding nothing. So in other words, the max material condition size of the hole is going to be the nominal size of the part, 625 thou. Now the least material condition size of the hole is a little bigger, and so it's going to be increased by. Now this does not mean 1 inch wiggle. It means instead thousandths of an inch. And if you take a look right here, all these values are shown in thousandths of an inch. So that's 1 thou. That 1 thou has to be added to 625 thou, so you get 626 thou. Then over here for the comparable shaft that will create that running clearance fit, the shaft has to start with the nominal size and get smaller in order to be a clearance fit all the time. So at the largest that the shaft can be is the nominal size minus 6/10 of a thousandth of an inch. Its least material condition is going to be the nominal size minus 1.3 thousandths of an inch. So let's go back and take a look at the calculation. So here we have the running clearance fit. This is the same table we just looked at, plus 1, minus 0.6, minus 1.3. So it's always a good idea to start by just saying, listen, I know I'm going to need a situation where no matter what I do when I make these parts is always a clearance fit. So it's always going to have a shaft size that's smaller than the hole size. So we come down here. First we're going to do hole basis. Under the hole basis, we're going to say that the size of the hole is going to be 625 thou. Put the 0 in because you're dealing with 4 decimal places with everything else. So 625 thou is the nominal size. Comes from here. And it's also the max material condition size for the hole. Now if we look up in the table, 0 indicates that the max material condition size of the hole is going to be the nominal size. The least material condition size of the hole is going to add a thou, 1 thou. So the two numbers we get over here are 625,000 and 626,000. Now we go over and look at the shaft. The shaft is going to also start with a nominal size, but if you subtract 6/10 from 625 thou, you get 624 and 4/10 thousandths of an inch. If you subtract 1.3 from the nominal size of 625, you get 623 and 7/10. Now that's how you calculate this on a hole basis. There are no tables for shaft basis. The tables are all for hole basis. So you start by doing the hole basic size. Now if you really want the shaft basis instead, in other words, you want to start with the shaft and then go to the hole, now the max material condition size of the shaft becomes the nominal size. And if you take a look over here, shaft diameter is 625 thou. Well, what was it before when we did the hole basis? When we calculated it, it's a difference of 6/10. So what did we have to do in order to get the shaft maximum material condition size from the hole basis to the shaft basis? We had to add 6/10 of a thousandth of an inch. Well, 624 thou and 4/10 plus 6/10 is 625 thou. If we're going to add that to that number, we have to add the same value to all 4 numbers in order to make the range consistent across the two different bases. So what happens when we add 6/10 down here? We add 6/10 to 623 and 7/10, which is what we had under whole basis, and we get 624 and 3/10. We go back to the whole now. The whole started at 625 thou. We add 6/10 and we get 625 and 6/10. Least material condition was 626 thou. We add 6/10, we get 626 and 6/10. Now those numbers are all going to give us the same relationship whether we're using the shaft basis or the whole basis. But you have to be able to maintain the relationship between the two sizes. Now when you're done calculating, you can check your work by looking back in the table. And in the table it says you've got a 6/10 clearance or a 2.3 clearance. So we take a look and say, well, what is the clearance at max material condition? Max material condition clearance is going to be the difference between this and this, which is 6/10, which is what it is. What's the difference at least material condition? Difference between 1 thou and 1.3 thou. Add those together, you get 2.3 thou, and that's the value you get over here. If you just come down and actually do the math down here, max material condition, if you subtract 624 and 4/10 from 625, you get 6/10. That's your 6/10. If you subtract 623 and 7/10 from 626, you get 2 and 3/10. So it's possible to check your work after the fact by looking at those values. Now let's take a look at the transitional fit. So you read the table the same way. I'll go back to the PowerPoint. So here we have the LT. LT stands for transitional. You're going to use this table in exactly the same way. You're going to locate the nominal size, the row for the nominal size, come across to the columns for LT1, and you're going to have, so 0.40 to 0.71, so 0.50 comes in between. So now the range of fit we'll use to determine whether you did the math right. So you've really got 4 numbers to deal with here. Now for whole basis, one of the numbers is always going to be 0, and that means you're going to start with max material condition size of the whole as a nominal size. So we come down here, and max material condition size is 0.5000, 500 and no tenths. And you look up here and it says for the other dimension for the whole, for the least material condition size of the whole, you add 7/10. You add 7/10 to 500 thou, and you get 507/10. Come over here and it tells you that you're going to add or subtract. This is what makes it a transitional fit. If you add 2/10, you get 502/10. If you subtract 2/10, you get 499 thou and 8/10. Now, if you take a look at that, at max material condition, you're going to have a slight interference because the shaft is 2/10 larger than the hole. At least material condition, you're going to have a clearance because the shaft is smaller than the hole is. Now that's for hole basis. To do shaft basis, you do the same thing we did before. Say in order for this max material condition size for the shaft to be calculated, we added 2/10. What we need to do now is to make that shaft size, the max material condition size of the shaft, has to be made the nominal size of the hole. So what would it take to go from 502/10 to 500? You have to subtract 2/10. So if you come over here, the shaft diameter is going to be 500 thou. Subtracting 2/10 from 499 thou and 8/10 will give you 499 and 6/10. Subtract the 2/10 over here, gives you 499 and 8/10 for the whole size. Subtract it down here and it's 505/10 for the least material condition size of the hole. So if you take a look at max material condition, you still have the shaft diameter being larger than the hole diameter by 2/10, which is what it shows right here. At least material condition, you still have the shaft being smaller than the hole, and the shaft is smaller than the hole by 9/10, which is the number that you see right here. So once you've calculated these values, you can go back up here to this column and determine whether or not your math is correct. So what you have to pay attention to in these values up here is whether it's plus or minus. You're always starting with the nominal size. So for the whole, you're going to do nothing to one end, and you're going to do something to the other end. So there's nothing added to 500 thou, and then there's 7/10. But over here, you might have a plus, you might have a minus, and for a transitional fit, there's usually one of each. Now, if we go down to the next class of fit, it's an LN. N stands for interference, so we have a situation where the shaft, in this case the outside of that bushing, is always larger than the hole that it goes into, which is also right there. Now again, you go to the tables and you find the location for the size, in this case 750 thou, and that's the row, and you follow it across until you find the columns with the class of fit, LN3, exactly the same way we did the others. In this case, though, you'll notice that there's a plus and then there's two other pluses. For clearance, the shaft got smaller. For transitional, it got smaller or bigger. And for interference, it gets bigger because the shaft always has to be larger than the hole. Now, hole basic size, we start off again with a 0. So one size, one end of the tolerance range is 750 thou, and that's the maximum material condition size of the hole. The hole can't get smaller. It can get bigger by how much? Plus zero point 0.8 or 8 tenths. So 750 thou and 8 tenths is the other end of the hole. The shaft, you're going to add 1 and 7 tenths or 1 and 2 tenths. 1 and 7 tenths is going to give you the max material condition size, so 751 thou and 7 tenths. Plus 1.2 is going to give you the least material condition size of the hole, is 751 and 2 tenths. Now in every case, at max material condition, the shaft is larger than the hole. At least material condition, the shaft is larger than the hole. Now if you're going to do and the difference between them, in this particular case, the difference is 1.7. Look over here, you have 1.7. Down here, the difference is 0.4. You look up here, your difference is 0.4, so we know that those numbers are probably correct. If we started with the shaft instead of the hole, that 750 thou nominal size has to be one of the shaft sizes. What would it take to get that from what we had calculated? You've got to subtract 1.7. You've got to subtract 1 and 7 tenths, thousandths of an inch from each one. So once you've done that to one, you have to do exactly the same thing to the others. It's always subtracting. And when you're done, shaft bigger than the hole, shaft bigger than the hole. Differences 4 tenths. The difference is 1.7 tenths.